Finally, we're going to move on to the next example, where we see how to actually build this model right. By the way, there isn't really anything wrong with the second model, it just wasn't a good model. This is unlike the first model, where there actually were things wrong with it, because it gave us misleading results and also predicts the wrong thing. In this final example, we are going to make use of all the data, open, close, high, and low prices, as well as the volume. So we are going to have a T by D input, where T equals 10 and D equals 5, and from this, we are not going to try and predict the return. Instead, we turn this into the simplest problem possible. Just try to predict whether the price will go up or down. In other words, binary classification. If you've worked in machine learning long enough, you should have some intuition about this. Regression is in general a harder problem than classification. With regression, you have to predict a continuous value. You can't be too high or too low, you have to be right on the nose. Classification is easier, especially binary classification. You don't have to predict the exact number, you just have to predict a label. In this case, you only have two choices, up or down. So this is what we are usually trying to predict when it comes to stock returns. Let's get back to the code. First, we are going to start by getting all the data into NumPy arrays. So the input data is going to be made up of the open, high, low, and close prices, as well as the volume. The target is going to be based on the return. Next, we are going to set n, t, and d, since our data is of shape n by t by d. T is simple, we can just choose that, so let's stick with 10. Although, in the future, you may want to try different values, like 20, 30, 40, 50, and so on. D is also simple. It's just the number of columns in the input data. N is a little tricky. It's the length of the series minus big T. Although this should remind you of each of our time series examples where we did the same thing. We just never calculated N explicitly. Next, we're going to normalize the inputs. This time, we're going to make it a little easier on our model. Instead of the first half being the train set and the second half being the test set, let's make the first 2/3 the train set and the last third the test set. So as usual, we're going to normalize our data. This is especially important now since the volume column is very high compared to the price columns. Next, we create our train set. X train is of shape n train by t by d, and Y train is of shape n train. Then we do a loop where t counts up from 0 up to n train, and we populate X train and Y train. For X, we take the input data from little t up to little t plus big T. For Y, we have a Boolean, which is true if the return at little t plus big T is bigger than 0. Next, we create the test set. As you might expect, n test is n minus n train. So x test is of size n minus n train by t by d. And y test is of shape n minus n train. Next, we enter a loop, counting from 0 up to n minus n train, or equivalently n test. Inside the loop, we actually have two indices. U refers to the index of x test and y test, which of course will start from 0. But remember, we are indexing our original data set, which must be offset by n train. So t is equal to u plus n train. And we use t to index the original data set, whereas we use u to index x test and y test. Once we're done that, we can make our RNN. Importantly, remember that we are now doing binary classification. What this means is that our model outputs are still the same because no matter what, our final layer will be a linear. What makes it different is the loss function. Our loss is now the binary cross entropy. So let's run this and train our model. So we trained for quite a while, 300 epochs. So what do we see here? We see that the train loss goes down a little bit, but the validation loss goes up a lot. So what this tells us is that the model is just again overfitting to the noise in the train set. So that's what it means when the train loss goes down, but the validation loss goes up. If we look at the accuracy, we see the same thing. The train accuracy goes up, but the test accuracy stays at 50%. Now you might ask, why doesn't the test accuracy go down? One important thing to realize about binary classification is that zero accuracy is not the worst accuracy. If your accuracy is 0, that means you can just reverse all your predictions and you would get 100%. That would be a perfect model. In other words, for binary classification, the worst accuracy is actually 50%, meaning it's no better than random guessing. That's why the test accuracy remains at 50% as the model overfits. Alright, so that's the end of this script. Let's now discuss and summarize everything we just did, since it was probably a lot to take in. We just went through 3 examples of predicting stock returns. In the first example, we used an LSTM to predict future stock prices from past stock prices. While this appeared to work well with a one-step forecast, it didn't work so well for multi-step forecasts. We saw that the model was likely just remembering the previous value and making that the prediction. This actually makes sense in the context of our second example as well, where we tried to predict stock returns. In this example, we saw that we couldn't get the loss to decrease that much. The third example we did was to consider all the data, not just the previous close prices, and to turn our model into a binary classifier. We saw that, even on the simplest possible task with the most data, the model still could not achieve better results than random guessing. What this tells us is that there isn't any hope of our first 2 models working in the first place. Imagine if you can't even predict whether the stock price will go up or down, how could you ever predict the numerical value of the return or the next stock price itself? In other words, if you can't even do the easy task, then surely the harder task is also not going to be solved. So be suspicious whenever you encounter an almost perfectly accurate stock price forecast. If we can't even do binary classification, then you can be sure that forecasting the actual price will not be so simple. By the way, these results should not be surprising. I asked you earlier to keep in mind the previous examples we did in this section. If you recall, we had trouble getting an RNN to predict a noisy sine wave. The underlying function in a noisy sine wave is a sine wave. It's a deterministic signal. You can imagine that if we have problems even with that, then in comparison, stock prices should be a huge problem. The major problem with trying to predict stock prices from stock prices is that it's a fundamentally flawed approach. These approaches don't take into account data about the world itself. Why does a stock price go up or down? Many times, it's due to some occurrence in the real world. Imagine how ludicrous it would be to say, here are some historical stock prices. From this, the future is totally deterministic. We can predict everything that will happen. Now that is a pretty crazy line of thought. Now consider a more realistic scenario, where stock prices depend on the emotions of investors. That could be based on things like how the company is being portrayed in the media, whether the company has invented something new, and so on. Even without knowing about deep learning, this should be enough to make you suspicious of any course that claims to be able to use LSTMs to predict stock prices using historical data. And yes, that's what a lot of people are doing out there, forecasting stock prices based on a time series alone. Instead, we can think about what actually might cause a stock price to go up or down. We see examples of this all the time. For example, when Facebook is being investigated by the government, that causes its stock price to go down. When Elon Musk tweets while intoxicated, that makes his company's stock price go down. But when someone at SpaceX invents a new kind of rocket technology, that makes the stock price go up. Imagine what you are saying if you try to use historical prices alone to try and predict future stock prices. That's like saying, using historical stock prices, you think you can predict whether Facebook will be investigated or fined by the government, that Elon Musk might make a stupid tweet, or that some rocket scientist will invent something. To believe that you could predict such events from looking at stock prices is surely a laughable idea. That's like saying different events that happen in the world are preordained by stock prices. Now that is crazy. If you really want to learn how to do good stock market predictions, that could be a course all by itself, never mind a lifetime of study. Finally, this clearly isn't to say that LSTMs are not good. LSTMs have proven themselves time and time again on tasks such as language modeling and machine translation. We've already seen how LSTMs can be used for image classification, which is an application you probably hadn't even considered. So I hope this lecture helped you understand sort of a bigger picture around deep learning and how to choose the right resources to learn from. There are a lot of marketers out there trying to get your attention, so try not to fall into their trap.